Curious Clinicians, a medical podcast that asks why. I'm Avi Cooper, and I'm joined, as always, by Tony Brew and Hannah Abrams. Good evening to you both.
Avi, Hannah, good to see you guys.
Hello, hello.
For the 101st time.
I don't know when we'll stop counting.
I don't think you ever stop counting.
So this episode, we're back to our regularly scheduled programming. And for episode 101, Hannah is going to tell us about a very alphabetical curiosity question, a sort of an alphabet soup of sorts. Why do we develop natural incompatibility to other ABO blood types? Like, why does that happen de novo? Hannah, what brought you to this question?
Yeah, this spaghetti ABO of a question. So I'm on my transfusion medicine month in my hematology oncology fellowship, and I was just going through this month, and I felt like we had to bring a transfusion topic onto the podcast because I think transfusion medicine is a specialty that many internists don't know that they can go into, even without hematology oncology fellowship. And it is just this amazing, fascinating world. It's a mix of logic puzzles and epidemiology and supply chain management. And so I suspect that there are people who listen to our podcast who honestly would love this as a field. And I just wanted to share honestly, my joy in transfusion medicine with our audience. And doing a month of transfusion medicine, really thinking about blood and blood product transfusions for a month, has kind of forced me to look more deeply at some of the stuff that I thought I knew about blood products, or the concept even that we transfuse blood products between people. And so at the heart of that is ABO incompatibility. I know most of us know that we don't generally consider it safe to transfuse ABO incompatible blood. And the reason for that is because of acute hemolytic transfusion reactions that can develop. But I never really thought before, hey, we normally don't make that many antibodies to things that we have never been exposed to before. And so why would this be evolutionarily conserved when in the setting of blood transfusions, it can be really dangerous?
Yeah, I love this topic because, for a number of reasons, but one of them is that everyone kind of knows about the ABO blood groups. They kind of know, like, oh, I'm O positive or A negative. And then the medical community knows you got to be careful about transfusing someone who has a different blood type. But I'm not sure that I ever thought about, well, how do you become sensitized if you haven't previously been exposed? Like normally for our antibody-mediated reactions, you have to have some prior exposure and antibody production, and then that re-exposure is what leads to the catastrophic event. And here, you can, with hemolytic transfusion reactions, have a reaction with the first exposure, and it can happen really, really quickly, like during the transfusion. So I think this is a really fascinating question, and I'm interested to hear more about how we got here.
Yeah, and we're going to take a whirlwind tour through transfusion history. But I think, we think a lot about a lot of these immediate reactions that we have are innate immune reactions. So things like to parasitic infections with eosinophilia, or something in which the antigens would very obviously be non-human and non-self. But the A and B antigens are clearly very common human antigens. And so it's pretty common. And so the question is, why would we have antibodies against these antigens we don't have that are more common in humans?
So we got to start somewhere, right? Are we starting at the beginning of the alphabet, the letter A, or?
We'll start with
like Sesame Street.
Yeah, we're going to start
for
with
Apple, or
A is for ABO. We're going to start, I think, with the development and the understanding of how we even got to transfusing blood in the first place, because ABO is at the center of the whole thing. And I think we need a little history to prove that these antibodies exist and describe how we know that what they are, how we name them, etc. So
when did this when did the whole notion of giving somebody a transfusion start?
Yeah, and I think there had been attempts to transfuse prior to this, but I think the best place to start is with the start of modern transfusion medicine in 1628. which is when William Harvey discovered the circulation of blood, which you can imagine is necessary to even conceptualize this idea of a blood
important.
transfusion. Yeah. And so shortly after that, people came up with this idea of trying to transfuse the blood, which was circulating. And so the first successful recorded attempt at blood transfusion happened in 1665 when Richard Lower in England was able to transfuse blood between dogs. 2 years later, Lower and Jean-Baptiste Denis in France each separately reported successful transfusions from lambs to humans. But as this idea proliferated, within 10 years, transfusing animal blood into humans was completely prohibited because of reactions, as you might imagine. And so that kind of put a pause on things until about 151 years later, in 1818, the first successful human-to-human blood transfusion happened. Dr. James Blundell transfused approximately 4 ounces of blood to a woman with postpartum hemorrhage from her husband. He then did about 10 transfusions over 5 years, about half of which were beneficial and half of which, as you can imagine, non-beneficial, to put it politely.
Yeah. So, I mean, I think there's 2 stats here that are not particularly encouraging. One is 10 transfusions over 5 years. It's not as though Blundell was able to,
He wasn't
prove
running
his
a blood
point.
bank.
Yeah, and there's an explosion of this new life-saving intervention. And the other is, of course, that there's only a 50% success rate. And my guess is the failures were pretty profound failures. We're not talking like, a febrile reaction. We're probably talking, big time reactions. So
You're much more likely to get bled then too, right?
Yeah, exactly. So you definitely need that blood.
They were working on the idea. They were getting there. I would say.
Yeah, so it took like 150 years for us to like re-explore. Like, what did we do next to figure out how to make them not so deadly?
Yeah. So what happened after 1818? Well, I will say that things remained dismal through most of the 1800s. So there are some records, some description that some physicians were trying to transfuse milks, like cow, goat, human milk. And then we developed saline infusions, which replaced milk in 1884. So another very important invention.
That's good.
But right at the turn of the 20th century, a doc named Karl Landsteiner theorized the idea of 3 human blood groups, which he named at the time A, B, and C, and later added type AB. And he theorized that these could be inherited, and the reason that some human-to-human blood transfusions had led to transfusion reactions. Based on that, Ludwig Hechtdoen suggested the idea of cross-matching blood between donors and patients in 1907. And then it was off to the races. So only, 350 years later, more or less. So about a decade after that, we learned that people with that blood group C are actually universal donors whose blood can be given to people of other blood groups. And so, and that AB is the universal recipients. So eventually group C was renamed to group 0 or O, and then to the letter O to maintain this idea of a lettering system. Within a few decades, we had discovered many of the other blood antigen systems. So the Rh group, which now claims the letters C, D, and E, some in big and little fashion, the MNS and P groups, and all the blood groups we now know of, like Kidd, Kell, Lewis, Lutheran, Duffy, I, H. You can see how we get to the whole alphabet.
I'll say some of us know that, some of us don't.
Okay, I'm actually totally teasing you. I didn't know about most of this before I was a hematology fellow.
But can we rewind to how did Landsteiner know, what was his insight to
It's a great
this?
question, and I don't totally know the answer to that history. But the idea was that there might be some genetic component to why some people's blood transfusions worked. There might be some inherited component.
Wow.
Yeah,
Prescient.
I don't know.
Prescient.
We should look into it more, actually. But
well, you mentioned all these blood groups that I'm Tony. I really haven't heard of. I had never heard of maybe I've heard of Cal. I had never heard of Lutheran.
Yeah, I definitely hadn't heard of Lutheran. The one that I've heard about sort of more recently is Duffy, because in the last few years, the transition to Duffy null associated neutropenia in those of African ancestry. But like these other ones, maybe I've heard of KID, but if you had sort of given me a list of 5 different words and said which 2 of
Random
these are
words.
blood groups, I would have probably had to just been guessing. Like these are not
like a
ones that
mocha.
would have rolled off my tongue.
Yeah. It's like a church or church daisy, red. Yeah.
But there's so many of
Yeah.
them, and I think for good reason. We as clinicians know about A and B and A, B, and O. So there must be some difference between these types of antigens that leads to them causing reactions, and also causing either more severe or less severe reactions. So, like, what's going on?
Yeah. So I'm going to tell you, but first I want to see. I mean, do you guys have any ideas?
I don't know, the recognition of the immune system, like how many of them are on the red blood cell. I mean, I could make some hypotheses, but I short answer is I don't know. I don't know if you know, Avi.
Yeah. So, I mean, I think the immune reaction piece, these kind of structural immune reactions are really the crux of it. So, Landsteiner and his colleagues, they worked backwards. So they found the reactions, and then afterwards they kind of deduced that there are groups, or Landsteiner and 350 years worth of people attempting blood transfusion. But thinking forward, right, the idea is to think about the physiology. What do we know now? And so all of these groups refer to molecules that are on the surface of blood cells, and in this case specifically red blood cells. And just like any other cell, we have a whole mix of stuff on the surface, which includes proteins and carbohydrates. And so the ABO antigens are actually carbohydrates, and the genes produce enzymes that generate the sugars, so cleave the sugars and put them on the surface of the cell. So you're either on the surface of your red cells displaying A antigens, B antigens, both or neither, and that's A, B, AB, and O blood types. And so we had to figure out these groups to figure out how to transfuse people safely, because they are, like you said, the most immunogenic of the blood groups.
And we spend so much of our time thinking about the A, the B, and the ABO, and Landsteiner. Those are the first ones that were discovered. But I feel like there's a plus coming, because we don't typically talk exclusively about the ABO. We usually talk about O positive, A positive, negative, whatever it is. And this is sort of the rhesus group, I believe. So like what is the significance of that antigen to these reactions?
Yeah, and RH or the rhesus group versus the ABO group are actually kind of helpful to compare and contrast. So the rhesus antigen, and specifically the D antigen, so the RHD antigen, is another very highly immunogenic antigen, which is why we talk about it so much when we talk about things that have to be empirically matched for a blood transfusion. And so to compare and contrast the two, the D antigen, so the RH group is a set of transmembrane proteins. And so unlike ABO, exposure to RHD mismatch works kind of like how we talked about earlier in the episode, how we might expect antigen development to happen. You don't have naturally occurring antibodies to RHD, but you can make IgG to the antigen if you're exposed to it at some point in your life, like with a blood transfusion or with pregnancy.
Okay, so we've got this sort of carbohydrate versus protein dichotomy here, ABO versus other. But if we have all these other blood groups, like why doesn't somebody's like blood donor card say, I am AB negative, KID positive, little I positive, Lutheran negative?
Well, it wouldn't fit on the
Yours
blood
doesn't,
donor
Avi.
cards.
That's exactly what mine says.
Yeah, we'd actually run out of ink to print the blood donor cards, because
Nailed
there
it.
are probably hundreds of these, right? So the reason is that the other antigen groups are much less often clinically significant. So we often don't empirically do our kind of electronic serial or our electronic cross match for them, because ABO is particularly immunogenic. And like we talked about at the beginning of the episode, we make our naturally occurring antibodies to those antigens very early on in life.
So we like, are we talking adolescence or?
I know that's
Like,
the youngest.
do my
patients I
kids
see.
already have these?
So here's what's wild. So we don't have them at birth, but we do have them by 6 months. So this is not something you're born with, but it's something you have to develop really early on in life. So most babies, about 80% of babies have developed these antibodies to whichever antigens they don't have by 6 months of age. And the maximum antibody concentration, you reach that around ages 5 to 10. They persist through most of life, although there have been some descriptions that in much older age, like age 97, they do decrease in concentration. And so you can imagine the average 10-year-old has not had a blood transfusion, hopefully. And so that means that these antibodies are developing without a specific exposure to the kind of human analog or human blood. And they're primarily IgM antibodies. We do have some IgG and even IgA anti-ABO antibodies.
So it's interesting. Like on the one hand, I feel like there are like lots of questions about this. Like one, if it's if we don't need exposure to other blood types to develop these antibodies, why aren't they present at birth? And then also, like, why are if we're not being exposed to it, like, why do we already have? Why does a baby start making antibodies against something that they've never seen?
Yeah, so we end up making...
And like enough antibodies to have an immediate reaction, right? Not just like a little bit, floating around, but like enough to, hemolyze.
Yeah, super strong antibody development. And it's not like, 10% of people develop these. Everyone develops these. So everybody must be having early on in life some exposure that allows them to make these antibodies, even if it's not necessarily the specific exposure to these blood groups. And so the answer is that everyone has exposure to probably some combination of things that allow us to make these antibodies. And then probably evolutionarily, I'll explain why they're important or beneficial to make so strongly. So two key kind of groups of exposures that people think are probably the drivers of babies making these antibodies. So the first is microbes through the gut, and the second is food. And so I'll say food first. As early as the 1930s and 1940s, actually, people had begun to understand that some foods are associated with hemagglutinins. So, for example, as early as 1948, scientists had identified that some legumes induced antibodies that were similar to anti-A antibodies. And I'll say that even if we didn't have the gut microbiome part that I'm going to talk about, we know that from mice that are grown up in germ-free conditions, they will still develop anti-ABO antibodies, probably from food and allergens.
Wait, so is there a scenario in which somebody is raised in a completely germ-free environment and they somehow avoid the foods that induce?
It has I don't think it's been reported.
It seems impossible. Like you know what I mean?
Talk about a very sheltered life. No legumes.
I'm not.
Well, and we'll link to the kind of more recent, this is a 2023 paper where they looked at the development of anti-ABO antibodies in these mice that had been raised in germ-free environments, because people had thought about the microbe part for a while that I'll talk about, but that they wanted to show whether it could be done in a germ-free environment too. And so probably this is important.
But they probably still had bacteria in their guts, right? I mean,
presumably. That is a key, I think, flaw of that paper. But because then the question really is like, why is this so conserved evolutionarily, so important that 80% of babies have this by 6 months old? Like, there's not that much stuff that we develop immunologically by 6 months to that degree of maturity and breadth of coverage of the human condition. And this is where the microbes come in, and probably the more potent answer also for the teleological, why does this happen, part of our episode. So it turns out that many different A-like and B-like antigens are present in bacteria and parasites.
Hmm.
And in early experiments, physicians tried immunizing animals with a variety of bacteria, including Salmonella, Shigella, and pneumococci, which all had slightly different names back then, and found that it can generate ABO type specific antibodies, which explains why we evolutionarily might have wanted antibodies to be able to recognize these before the first time that we see them. They were later identified to probably be similar to surface polysaccharides. So again, the sugar, the carbohydrates on the surface of the red cells, probably similar to surface polysaccharides that are on these different bacteria. And similar carbohydrates are also present on the surface of red cells from a variety of different types of animals, which explains why xenotransfusion, the lamb transfusion that was attempted, also causes similar reactions.
This is very reminiscent of other discussions we've had on the podcast where we've talked about scenarios where human immunity and then potential autoimmunity is sort of linked to an antigen in an evolutionarily important microbe. I mean, not all microbes are evolutionarily important, but certainly malaria is, and certainly group A strep is. And Avi, in episode 65, you kind of taught us about how in the case of rheumatic fever, it isn't necessarily destruction by the microbe, but rather the immune destruction because of similarities between the the M protein of group A strep and human myosin and laminin, and sort of this cross reactivity. So it seems like this comes up in a bunch of different places in the human body.
Yeah, the other carbohydrate that we've talked about is alpha gal,
Right.
right?
Another consumptive one too.
Right, exactly. And so the thought being, the sort of the alpha gal story was related to protection against, so similar to this, protection against viruses from other animals.
Yeah. And this one's also a carbohydrate. So
It's really like compelling, this idea that the human body is going to prepare you for exposure to these pathogenic organisms even before you've seen them by placing an antigen on the most ubiquitous cell in the body and just say, body, go make some antibodies to this, because at some point in the near future you're going to be exposed. Like that is a fascinating hypothesis.
yeah, and I guess this idea that, like, well, the counterexample, if you didn't make these antibodies, sure, you might be able to survive a blood transfusion, which we have not done except for the most recent 400 years of human history. But you might not recognize pneumococcus in your blood, in your blood until it's too late. And what's really one thing that's really fascinating about this is, so cold autoantibodies, these IgMs, all of us make tons of these. Like, one of the transfusion faculty in our program likes to say that probably if you took everybody's blood and you cooled it enough, you would find some IgM against something that we could test for on a panel. And many of these are specific to certain bacteria or parasites, like leishmaniasis, like, for example. But ABO, the ones that have this ABO homology, must be common enough and deadly enough to have become so evolutionarily preserved that we make these super high titers and that we reliably generate them almost every human. And evolution just really hasn't had the opportunity to catch up with this idea that now in modern medicine, where we have antibiotics and we have blood transfusions, it's actually a little bit of a drawback.
Yeah. So is it molecular mimicry? Like, is that the problem here, essentially? That, like, our red cells look too much like, or like a blood group antigen, like on a incompatible blood type, looks too much like a pneumococcus carbohydrate sort of thing. Like, we've got these antibodies and our body can't tell the difference.
Exactly. That's probably the idea, or that it's so important for us to be able to recognize pneumococcus that we're like a little non-specific about making antibodies to stuff that even looks a little like pneumococcus.
I mean, it sounds like intentional mimicry, the beneficial mimicry. Like, we want to make these antigens so that we recognize the bacteria.
And it does work pretty well for us because for the most part, most people don't need blood transfusions during their lifetime.
Right.
Just in the modern era, this is a thing we do now.
Did you look at all into whether or not those who are group O and so don't make these antigens are more predisposed to some of these pathogenic bacteria?
I didn't. Although, so people who are group O make both sets of antibodies.
Oh, I'm sorry. Yeah.
So it's group AB.
Right. Group AB.
It's a great question. I will say there was actually a ton of research during COVID. The kind of level of rigor of which I cannot confirm, but a ton of research during COVID about blood groups and susceptibility to viral infection.
Yeah.
That you guys might remember.
Oh, I'm sure. Yeah. I don't remember all the details, but
yeah, I mean, there was so much going on at that time, but there is probably a lot we don't know about the relationship of the immune system with these kind of red cell antigens. And I also, kind of bringing it back to Duffy, I'm going to put in a plug that we should do that as an episode. But I don't actually know why not having Duffy B causes neutropenia or low neutrophil count.
Anything else? Other interesting facts about blood groups that you want to share?
Yeah, just blood facts. Okay, one more.
You did a month of transfusion medicine, so
I know. This month honestly exposed me to so many unknown unknowns about the world of transfusion, including how many blood groups there are. I do have one more fact though, which is that, so I mentioned that a lot of neonates, the large majority of neonates, don't have these antibodies yet, even though the large majority do by 6 months. So then I did wonder what that means for the health and medical management of these neonates.
So, and I guess it makes you wonder, like, if it takes until 6 months of age to make these antibodies, are they protected against ABO incompatible transfusions? Like, could a 1 month old baby safely get an incompatible blood type?
Yeah, okay. Yeah, tell us, please.
So I asked that question, and first of all, it turns out that babies get blood in like milliliters per kilogram. So if there's not exactly a shortage of the amount of O-neg blood that is required to transfuse babies, because they need very small amounts of it. But it is theoretically known that, for example, if there's like a lot of passively transferred allo antibodies from mom, that babies probably can be given, there can be a little bit of mismatch there, it's thought, because of that. Although I will say in one study, there was some prevalence of anti-ABO antibodies even in that early phase. So I think that's for many reasons why people don't do it. But here's the amazing thing. In a resource that is much more constrained, which is heart transplants, it has been shown that neonates under a year old can be transplanted with ABO incompatible heart transplants without developing acute rejection, even when they had known ABO antibodies. So coming back to alpha-gal and the goal of transplanting and the way that these surface carbohydrates really affect our ability to do heart transplants, these like 10-day-old, the first case reports I think were in a 10-hour-old and a 14-hour-old, and they were able to be transplanted with an ABO incompatible heart without developing hyperacute rejection.
That's just so fascinating.
Mind-blowing.
Amazing stuff.
Hannah, I do hope that you're not going to quiz us on all the human antigens as part of your take-home points. And assuming that is the case, can you give us some take-home points?
I solemnly swear not to quiz you.
Raise your right hand.
I mean, even if you do, I'll fail.
Yeah, I guess that's what heme boards is. I don't know. But some take-home points. So first is that humans develop anti-ABO antibodies, especially IgM, very early in life, without requiring prior exposure to these antigens. We do this because of similarities between the AB carbohydrates and antigens on bacteria, parasites, and probably in our food. This is distinct from many other types of antibodies that we form to non-self blood groups because this does not require prior exposure, and those others typically or often do require prior exposure and primarily form IgM or warm antibodies.
Well, that wraps up another episode of The Curious Clinicians. Claire and Morgan of Nautilly.com is our audio editor, and Giancarlo Bonomo is a producer for the show. You can join our mailing list at curiousclinicians.com to stay up to date on episode releases and have detailed notes delivered directly to your inbox. You can also subscribe to our Substack at thecuriousclinicians.substack.com, and you can watch a video of this episode on our YouTube channel, The Curious Clinicians Podcast. And as always, the information contained in this episode is for educational and entertainment purposes only and does not constitute medical advice. Until next time, we've been The Curious Clinicians.